Hello everyone, we're Yucheng and Olivia, and we're here to present our work, Auto-Tuned Sim-to-Real Transfer. As of late, we've seen a lot of incredible success in the field of robotics in the real world. But what these videos don't show you is that oftentimes behind every successful robot, there's a team of even more successful control engineers. But if we desire robots that are able to adapt on their own to the unstructured and uncertain nature of reality, we can't rely on there always being such a team of engineers to dictate what each robot should do in every possible situation. Reinforcement learning has been proposed as a solution to this problem by enabling agents to learn on their own how they should behave through interacting with their environments and receiving some form of feedback through an external reward. For robotics in particular, however, it's oftentimes expensive and potentially dangerous to do this learning directly in the real world, and so usually we replace the environment with some simulator. And so this whole system of using reinforcement learning and learning primarily in sim has led to a lot of success as of late for real-world robotics tasks as well. But this approach still has its limitations. In doing most of our learning in sim, we encounter a secondary problem called the reality gap, where policies learned fully in simulation won't work when directly applied to the real world because our simulators are not rich enough to accurately and fully capture reality. So there may be discrepancies in the way the world looks or in the dynamics and so on. In order to cross this reality gap, many methods have been proposed, and a prevalent method is domain randomization. In domain randomization, what we do is we take the set of simulation parameters and randomize them enough such that our policy becomes robust to small changes in these parameters, and will as a result work in the real world even though we don't know what these parameters are exactly. But in order to get domain randomization to work, not only do we have to specify all the parameters that we want to randomize, we also have to be careful about how much we randomize them by exactly. If we don't randomize them enough, then the policy ends up not receiving the robustness benefits we desire. But if we randomize them too much, then the policy ends up becoming overly conservative and won't work either. And so it seems like we really shifted this problem further. We've gone from doing a lot of control engineering to get the robots to work in the real world to now doing a lot more simulator engineering in order to get our policies to transfer to real robots. And so the problem that we aim to tackle in this work is really reducing this amount of engineering required and take some steps towards full automation. There's been a lot of exciting new work in this area as of late, leveraging some amount of real-world data in order to close the reality gap and reduce the amount of simulation engineering required, whether this is through trajectory matching, where we change our simulators such that trajectories in sim better match real, doing real-world modeling, or by training multiple policies and evaluating them in the real world. But what all of these methods have in common so far is that they require some amount of motion tracking or object tracking in the real world. And so we still need to instrument the real world as a result. And once again, it seems like we've shifted the problem one step further. We've gone from control engineering, then to simulator engineering, and now to real-world engineering in order to get these robots to work in the real world. And so the question we really want to answer here is, well, can we remove that entirely? Can we use some amount of real-world data without instrumentation in the real world to improve our simulators, hence auto-tuning them? I'll pass it on to Olivia here to talk more about our specific method and our solution to this problem.
Our goal is to tune a simulator using only image data and no instrumentation in the real world. In this paper, we design an auto-tuner, a module which takes in an untuned simulator and some real-world trajectories, then outputs a tuned simulator which closely matches real-world visuals and dynamics. First, let's look at a naive approach to designing this auto-tuner. The simplest way to tune our simulator would be to design a regression module which takes in real-world videos and directly outputs a scalar value for each sim param. The first challenge is to train this module. A natural approach here would be to train the model with a domain randomized simulator. We can collect a diverse set of videos paired with the ground truth sim params which produce them, then directly train our regressor using supervised learning. Unfortunately, this naive approach fails in dynamically complex environments, where training a model to directly predict the precise values of dynamics parameters is very challenging. Instead, let's consider a simpler problem. While identifying the precise value of a parameter is hard, identifying which of two trajectories has a higher value is relatively simple. Inspired by this observation, in our method, we replace the regression model with a classifier, which takes in a video trajectory and a vector containing one candidate value for each sim param we're tuning, then outputs the probability that each candidate sim param was higher than the ground truth parameters which created the video. Unfortunately, directly training this classifier doesn't work well either. Sim params are scalar values on very different scales, and it's challenging to find an appropriate normalization because the real-world parameters we want to consider might be out of distribution from our naive initial simulator randomization. To address this, we encode the sim params using positional encoding. Positional encodings have been a crucial part of many recent successful ML models, including transformers and NERF models. The key idea behind them is that scalar values can be represented as a vector of sinusoids of varying frequencies. This gives us a unique encoding where all scalar values, including those which are out of distribution, are represented at the same scale. In our work, we individually positionally encode each sim param before it's passed into our classifier. After making these changes, we can still train our classifier in simulation using domain randomized video data and an independently sampled set of candidate sim params. From these, we can compute ground truth binary labels for our classifier, and we can train the model with supervised learning. So now we've shown that we can train a sim param classifier, but to actually use it to tune our simulator, we need to rethink auto-tuning as a search problem. Our simulator's domain randomization is parameterized by a distribution over each sim param. These distributions might start out far away from the true real-world params. First, we train our classifier on simulated data. To use this classifier to update the simulator, we pass in a real-world robot trajectory along with the mean of the current simulator distribution. We can interpret the classifier's prediction as the direction we need to update our simulator to move it closer to the real world. We update each parameter slightly in the appropriate direction, then repeat the process until the mean of our parameter distribution converges to real-world values. There's still one piece missing before this algorithm works correctly. Unless the robot interacts with an object, we won't get the data we need to tune our simulator on that object's dynamics. To make sure the robot handles every relevant object, we train a policy in simulation in parallel with the auto-tuning process. Unfortunately, doing this introduces its own challenges. Our sim param classifier trains best on a large, diverse dataset of different parameter values. However, it's a known problem that policies which are trained on across too wide a distribution of dynamics parameters end up overly conservative. On the other hand, if we store a less diverse data buffer, our policy trains well, but our classifier won't be able to predict well on out-of-distribution real-world values. To fix this, our insight is to collect separate buffers, a less diverse policy buffer, which changes slowly as we adapt our simulator, and a much more diverse sim param buffer used to train our classifier. To recap, our method integrates three insights: thinking of tuning as a search problem, positionally encoding sim params, and storing separate buffers for our policy and classifier. Finally, let's put this all together into our full pipeline. We start with an untuned simulator, from which we collect domain randomized data for our two buffers. We train the policy on the less diverse buffer, and the classifier on the more diverse sim params buffer. Next, we run the policy in the real world to collect video data. This real-world trajectory, along with the positionally encoded mean of the simulator distribution, gets passed into our classifier, which outputs the direction to update each sim param to move it closer to the real world. Finally, we adjust the simulation's parameter distribution slightly in the appropriate direction, and then repeat this process until our simulation parameters converge to the correct values, and our policy succeeds in the real world.
Now that we've explained our method, let's evaluate it with some sim-to-real transfer. As a proof of concept, we first look at sim-to-sim transfer, where we take a set of simulation parameters and designate it as a pseudo-real world that we try to transfer from some set of different simulation parameters into. We look at a suite of different robotics tasks ranging from locomotion to manipulation. On this side here, we see the success rates and rewards across all of these different tasks. We primarily compare against the baseline of domain randomization, shown in blue, which, as you can see, doesn't successfully transfer to high success rates or rewards in this pseudo-real world. As an upper bound, we also train an oracle, which is the policy that's directly trained in the pseudo-real world and represents an upper bound for how well the policy can do if it knew each simulation parameter exactly. As a secondary baseline, we also run our method with the regression approach where we try to predict each parameter directly. And as we expected, this is much harder to do than the classification approach. And so although we see some improvements over the domain randomization baseline, we don't make that much progress towards the oracle line. Last, we run our method where we use our classification-based approach, and we see that we're able to beat out both baselines and make significant progress towards reaching the oracle, although there's still some gap there to close. So with this sign of life in mind, we then tackle the real task at hand here, which is sim-to-real transfer. We look at some tasks where it's difficult to directly simulate the task in simulation because of properties like using deformable objects like rope. So first task we look at is this rope peg and hold task, where on the left we see some domain randomized variance, and on the right we see what happens when we try to transfer a domain randomized policy directly to the real world. Essentially we see here that it doesn't transfer at all. But with our method, we find that we're able to improve upon this policy and successfully transfer to the real world after just a couple of simulator updates. We see this policy making more and more progress towards reaching the whole until it's eventually able to succeed at the task after 5 simulator updates. And so this is a video of the successful real-world transfer. The second task that we look at is this cabinet sliding task, where once again it's difficult to be able to predict what the cabinet friction and properties are just by looking at videos of it. Once again, we see with our domain randomization baseline, the robotic policy doesn't really transfer to the real world, and even though it tries to reach towards the cabinet, it doesn't open it at all. And once again, running our method, we see that with a few simulator updates, the policy is able to perform better and better in the real world, reaching the handle of this cabinet, eventually attempting to open it before succeeding at finally opening it after 6 simulator updates. And so once again, we see a video of the successful transfer of this policy to the real world after using our method. So in summary, we present our method auto-tuned sim to real. And our key insight here is really to reframe system identification as an iterative search problem in order to automate it. We do this using 3 key components: binary search for the simulation parameters, position encoding in order to account for outer distribution parameters, and using separate buffers for training the policy and the parameter model. In doing so, we show success at auto-tuning a simulator with minimal human involvement required. And as a result, we show improved performance on real-world robotics tasks for sim-to-real transfer. Thank you all for listening to our presentation.